Maureen Muldoon is a hydrogeologist from Wisconsin Geological and Natural History Survey. Her work has focused on using geological knowledge to better understand groundwater flow system in Wisconsin. And without further ado, Dr. Maureen Muldoon.
Thanks, Kulong. I'm Maureen Muldoon. Everyone calls me Mo. I worked for the state survey from 1987 to 1998. Then I was at UW Oshkosh for 21 years. And then in 2019, I returned to the survey. As you said, I'm a groundwater specialist. And so a lot of my research has focused on how groundwater moves in fractured rock aquifers, specifically fractured carbonate aquifers. And so I'm basically taking those 35 years of research and summarizing it in 20 minutes, plus maybe a little bit. But so there's going to be a lot in here. But let's get going. So, okay, so advance the slide, enter. It's not liking it. Advance. Okay, so what we're going to do today in terms of the talk is first just define what karst means. There's a lot of confusion about that. And then we're going to look mainly in Northeast Wisconsin to look at karst landscapes and flow characteristics because we have a lot more data up there. And then we're going to go through basically, since the second half of this focuses on groundwater quality, what are some of the things that really control groundwater quality in karst settings? And that'll be in Northeast Wisconsin, really soil thickness. Recharge and water quality are really both Northeast and Southwest. And then in the Southwest, well construction is very important. And then we'll do a little summary and takeaway points. So the picture you're looking at is the picture of the Silurian dolomite in Door County up in Peninsula State Park. And it's good to have a good mental picture of what the rocks look like, because basically when that's underground, that's what the water's flowing through. Okay, so just what is karst? And again, this is a picture from Door County in the background, and you can see very nicely some fracture traces in this field. But essentially, karst is a landscape or a type of topography that's formed on rocks that dissolve. So either limestone, dolostone, sometimes gypsum, and basically dissolution or dissolving those fractures and making them bigger is the key characteristic of this kind of landscape. And it's not like a single thing. It's not the fracture. It's the whole area where you have that bedrock near the ground surface. So it's a range of landscapes. Door County, you basically have fractured dolomite, and we'll look at that in a little more detail. If you've ever seen those weird pictures from China where there's just little pillars of limestone and everything else is eroded away, that's like really, really, really mature karst in China. In the US, it's pretty significant. It's about a fifth of US land area, and east of the Mississippi, there's a lot of carbonate bedrock near the ground surface. And so it's about 40% of the land area east of the Mississippi, which is certainly where we live. Now, since karst is basically what forms on top of bedrock, we need to know something about the bedrock geology of the state of Wisconsin. And here's a map showing you that geology put out by the state survey. This is our page size map. And I'm going to just really briefly walk through this geology. So let's start with this old stuff down here, all these brightly colored units. That's this. Those are Precambrian rocks, very old crystalline rocks, typically like granites and volcanic rocks and metamorphic rocks. And that's kind of not what we're worrying about today. We're worrying about this package of sedimentary rocks that's on top of it. So I'm going to direct your attention to this cross section down here. It goes from the west side of the state to the east side of the state. It's as if you took a knife and cut into the state of Wisconsin and could see the geology. And so what you're looking at is in these tan units, this is a sandstone. This is all of these formed when Wisconsin was much further south near the equator and we were covered by an ocean. So you start in the Cambrian time period with sandstones. This is about 560 million years ago. And then as you come up through time, you get a package that's kind of mixed. This blue unit is the Prairie du Chien dolomite, soluble. Then we have another sandstone, the St. Peter. Then we have the Sinope group dolomites, also soluble. Then we have a shale. And in eastern Wisconsin, we have the Silurian dolomite. So it's this big, thick package of sedimentary rocks that gently dips into the Michigan Basin and gently dips to the west. Okay, so how do you turn that into karst? Well, you take the bedrock units, the Silurian, the Sinope, and the Prairie du Chien, and if they're the uppermost bedrock unit, you then look at like how thick are the sediments on top of it. So in this map, you basically the state survey mapped out where do we have carbonate rocks, Where is it less than 50 feet to the ground surface? Those are shown in orange, and you can see all of southwestern Wisconsin, and a good portion of the western counties are in that area, and then parts of northeast Wisconsin. And then in the brown areas, you have greater than 50 feet to rock. So this is a good figure from Door County Soil and Water Conservation Department. I put this in the links that I shared with the conference organizers. This is what it looks like in Door. You've got fractured rock with very thin soils on top, and this is the Silurian dolomite. In the Southwest, this figure is from Minnesota, and the Minnesota Department of Ag has put out some great videos about how groundwater moves in southeastern Minnesota, which is strikingly similar to southwestern Wisconsin. And I would really suggest you take a look at those for trying to understand how groundwater moves in these environments. What's different in the Southwest is that you have this uppermost limestone, but then you have a shale. And that really affects the flow system. And we'll talk about that a little more when we talk about southwestern Wisconsin. In Door County, you have about 600 feet of dolomite before you get to a shale. And so just the groundwater acts a little differently. Okay, so what does southwestern karst look like? Here's an area that was never glaciated. You have a very, very weathered dolomite as your uppermost unit. You get things like conduits, little tubes. You get big caves like Cave of the Mounds, and you get sinkholes like this big sinkhole that's noted near Blue Mounds. The carbonates weather to form sort of a reddish clayey material that we call the Roundtree Formation, and that's sort of characteristic of southwest Wisconsin. Now we're going to start by looking a little more at northeastern Wisconsin and sort of what does that flow system look like. Here's the outcrop pattern for the Silurian dolomite. It's along eastern Wisconsin. Notice this nice kind of bowl shape. It comes up through the UP, comes down over here, makes Niagara Falls, and is also present in Ohio and Illinois. So it's kind of this circular outcrop pattern. And this is what it looks like. This is from a quarry in Door County. And I hope what you can see is that there's some pretty specific joint sets. There's one that runs like this and like this. Those are your vertical joints. And then there's all these bedding plane partings or fractures that are also present in this environment. And just sort of highlighting that a little more, this is what the top of the dolomite looks like in Door County. There are fractures every 15 to 20 feet. This particular field is an alfalfa field, and so alfalfa is kind of deeply rooted, and so over the fractures where a little soil's washed in, it's a little happier during dry conditions, and over the blocks, it's not quite so happy. But it's not like these fractures magically stop at the end of the field. They're just not expressed in this crop, which is more shallowly rooted. So vertical fractures are everywhere, and when you think about the Silurian dolomite, you should think that the top of it looks like that. And then when we go down into the dolomite, this is a picture, it's kind of a weird picture. It's a 3-inch core hole, and we're going down with a television camera that's giving you a 360-degree view. And so that circle that you see coming in is an open bedding plane fracture that's open about 1/4 of an inch. So there's big fractures that are horizontal in this aquifer. What that leads to is an exceedingly well-connected network of fractures, and the water moves really fast in those fractures. So I'm going to just skip all the research that tells you why this is true and just tell you what the flow characteristics of that aquifer are. There's a dense and ubiquitous fracture network. It's like this picture. Fractures are everywhere. And so there's very little surface runoff in Door County. The water essentially just infiltrates very quickly into the subsurface and straight down to the water table. The flow in that aquifer is not going through those blocks of dolomite, it's going through the fractures, and the flow rates are fast, like tens to hundreds of feet per day, which is just rocking it for groundwater. Recharge, which we're about to talk about, it's the process by which you take water from the ground surface into the aquifer. It happens really quickly in this aquifer, but it's not uniform throughout the year. It varies seasonally. So that's another feature of that characteristic. And low effective porosity can lead to really large variations in water level, and sometimes you get little groundwater mounds developing, which cause flow reversals. And we're not gonna go into those details at all. Okay, so let's look at what's going to affect water quality in these areas. First of all, you have soil thickness, and that's true in northeast Wisconsin. And then we're going to look at recharge, and we're going to use examples from northeast Wisconsin, but it's true in both northeast and southwest. This is a picture of spring runoff in a farm field in Brown County. That's how much soil you have, right? And the snow is melting, and everything that's been put on the landscape in winter is melting with it, and it's all being carried down and then just shooting into this little fracture and directly into the aquifer. There's no filtration whatsoever. These are some old data. This is from the Northeast Wisconsin Karst Task Force report back in 2007. I also put this link in the ones I sent. And what you're looking at is the state groundwater susceptibility map. And some of the characteristics used to make that map are depth to rock and type of superficial materials, and depth to water table. But what we're going to really worry about is the depth to rock, because this really expresses why you have water quality issues in this area. So in Door County, most of the area, it's maybe less than 3 feet to rock. And we're looking at bacteria here and nitrate here, and the black dots are the bad dots. So it's kind of a mix in Door County. But when we come down here where you start to get pretty thick soil covers, notice that most of your black dots are lining in the red areas. And it's even more true for nitrate. Here's the red areas, here's all your black dots. Here's the red areas, here's all your black dots. Red areas, black dots. I mean, we kind of know that thin soils are where we see groundwater contamination in these environments. And the study that really helped us sort of put some numbers on that understanding is the groundwater study in Kewaunee County back in 2015 and 17. So Mark Borchardt and I and Randy Hunt were the leads on that. At the time I was at Oshkosh, and there's a bunch of people in Mark's lab and at the USGS and in Kewaunee County who helped with that work. And I'm not going to go through the whole study because there's a lot to it, but I'm just going to go through one objective of that study. And again, I put a link to this final report in the links that I gave you. So the big first objective was to figure out, using indicator statistics like total coliform, E. coli, and nitrate, what is the extent of groundwater contamination in Kewaunee County? So if you look at all the private wells in Door County, estimating based on number of parcels where people live, there's a little less than 5,000. From those 5,000, we randomly selected 621 wells to sample. And that's the results I'm going to show you. The rest of these, in terms of figuring out where the fecal material was coming from, we're not going to go into that, okay? So here's objective 1, countywide random sampling of private wells. But because we knew that depth to bedrock was probably going to be an important characteristic, we stratified our sampling such that we sampled equal number of wells from 0 to 5 feet, depth to rock, 5 to 20, and greater than 20. And this is the map showing those depths to bedrock. This is less than 5, 5 to 20, and then greater than 20 in these areas. And the little gray things are parcels. We sent letters to people asking them to participate. We actually got a pretty high participation rate, about 50%. We sampled at 2 times of the year. And by synoptic sampling, I meant like over 2 days, people could bring their samples in. So we were trying to sample at single points in time, not spread out over the year. We sampled during a groundwater recharge event in November of 2015, and we had about 317 wells in that sampling event. And then a time period where recharge doesn't go into the aquifer, and we're going to get to recharge in just a second, where we sampled about 400 wells. And what did we see? It was pretty striking. Okay, for wells that were 0 to 5 feet, during the recharge time period, half the wells either had coliform bacteria, E. coli, or high nitrate. And during the non-recharge periods, it was 33%. Now look what happens as soil deepens. Our numbers go to 42% with problems and 40% with problems. And by the time we get to 20 feet, we're down at 23% and 26% with problems. And this is about the statewide average. So it really, really, really is depth to bedrock in Northeast Wisconsin that affects vulnerability. Now, I've been mentioning recharge a lot, but I haven't really defined it. But you guys all know the water cycle. We live in Wisconsin, right? So it rains. That rain can either run off or soak in. Sometimes it's held as snowpack, and then the snowpack melts. What I'm showing you here is some data from 4 wells in Northeast Wisconsin. The red is Kewaunee, the yellow is Brown County, the green is Manitowoc, and the blue is Calumet. This is from September of 2007 till August of 2008. We're measuring water levels in these 4 wells. The water levels are recorded every 30 minutes using a a pressure transducer and a data logger. And so you can start to really see when do water levels change. And not surprisingly, when water comes into the aquifer, the water levels go up. Okay, so we did this study after the Northeast Wisconsin Karst Task Force report, and we know that Door County is very vulnerable, but we wanted to look at areas that had somewhat thicker soil cover. So at these 4 wells, the soil thicknesses were 7 to 18 feet. What you see is in the fall of the year, once all the crops have been harvested and all the trees go sort of dormant, if you have a large rainfall event, it's going to go straight in. So here's an October rainfall of 1.5 inches, and we see a water level rise in almost all the wells. That year, we had a little bit of a melt event in December and a little melt event in January. The water levels go up. Okay, what's happened over the last week? All of this water went into the aquifer. It's not being used by plants. It's not evapotranspiring. It's pretty much going in. Okay. In this particular year, the major snowmelt event was in March, and you see those continuously rising water levels. Now, 2008 was a weird year. We actually had a summer recharge event. I live in Oshkosh, Wisconsin. We got 13 inches of rain in 2 days. There were people canoeing in the intersection about a half a block from my house. This is abnormal. Normally, water levels fall all the way through the summer, but we had a recharge event that year. So if you look at that whole year, there's not that many time periods where the water is actually going in, right? In this time of the year, like in summer, it rains, but the water goes into the root zone, and then it's evapotranspired back out by crops. And this really matters in terms of groundwater vulnerability, because we have to think about what are we doing on top of the landscape during these recharge times. Okay, I just want to show you one example, kind of an extreme example of water quality variation and recharge. This is from Kewaunee. So we have 2 wells here, this one and this one by the fish hatchery, that are both very shallow. We measured water levels and water quality at those non-pumping wells. We had a sampler at a homeowner's well where the casing, the metal pipe, went down to 200 feet and the well was 300 feet deep. And we were going to try to see what happened to his water quality during a big rain event. Okay. And we were actually analyzing for microbial targets. Okay. So this is the setup. Here's the guy's basement. Here's his pressure tank. This is a very very thorough system where we're measuring water quality parameters in a little exosonde here. The water is constantly running through our system. And then if it looks like it starts to rain, we can open the line to these various filters and we can filter water through them like a couple hundred gallons to look for pathogens. Okay, what did we see? Here's our non-pumping well. It starts to rain at 8 o'clock in the morning. We're going to get about 1.5 inches of a rainfall event. Our water level in that shallow well starts to rise 5 hours later. The water chemistry at that shallow well, we're measuring dissolved organic matter, which is basically when you see this come through, you're looking at soil moisture that's sort of being pushed by the recharge water into the aquifer. And after that soil moisture comes in, you get a decrease in the organic matter. That peaks about 30 hours after the start of the rainfall event. Okay, now to look at this homeowner's well, which remember, the water table is only at like 20 some feet. The well is only open at 200 feet. What we see is that coliform bacteria, which is at the ground surface, sort of peaks in about 30 hours. This is a log scale. So this is 1, 10, 100 colonies of coliform bacteria. So we're seeing that water hit the top of the water table and penetrate 200 feet into the man's well in a little over a day, which is really, really unusual for groundwater. Okay, so recharge. It's the process that moves contaminants from the ground surface into the aquifer. It varies seasonally, and that is when aquifers are most vulnerable. Most of the recharge occurs in early spring. However, fall and winter melt events can be significant, and it's rapid. All the wells in Northeast Wisconsin respond within 1 to 2 days of significant rain or melt events. And this can lead to huge variations in water quality over short periods of time. Okay, so now let's look at well construction, and we are getting close to the end here. Okay, so Southwest Wisconsin is a different kind of karst. It's different geology. So the Silurian dolomite is up here. In Southwest Wisconsin, this green color is a dolomite. It's the Sinope dolomite. It's this. It consists of the Galena, Decorah, and Platteville formations that are primarily dolomite. And then we have this unit called the Glenwood, which is a shale that provides some separation between this upper aquifer and the underlying St. Peter sandstone aquifer. People use both of these as water supply aquifers in southwest Wisconsin. But the main thing I want you to take away from this picture is that the geology is more variable in southwest Wisconsin. Instead of 600 feet of pure dolomite, you get like dolomite, sandstone, shale, dolomite, sandstone. It's a lot more lithologically variable. What that leads to is actually separate aquifers to some degree. So this is some work done by Madeline Gockwitz and Jonathan Carter down near Governor Dodge State Park. And what they showed is that this upper aquifer that near the edges of hills and stuff, there is sometimes actually a perch zone before you move into the deeper St. Peter and Prairie du Chien aquifer. And they're trying to show this in this picture where you've got this upper aquifer and this spring comes out very high up on a valley wall, makes a waterfall, and then flows over here to the more regional aquifer that is the St. Peter aquifer. Sue Swanson, our new director, and I did some similar work in southwest Wisconsin. We were looking at springs that deposited calcium carbonate called tufa mounds. The spring is way up on the side of the hillside. The regional water table is down here by the Grant River. That's Sue Swanson for scale. So you have separate flow systems in southwest Wisconsin. We did a study very similar to the Kewaunee study in southwest Wisconsin. It's Grant, Iowa, and Lafayette counties. It was initiated by those counties. The people responsible for doing the work are Ken Bradbury and Mark Borchardt, who are both retired now, and me and Joel Stockdick up at Marshfield. This is sort of showing you bacteria in terms of percent positive for those three counties. These are data prior to our study. And you can see the data were pretty sparse in Grant and Lafayette County. And that's really what motivated this study. And I'm just going to give you the takeaway message from it. Okay, here's a picture of the rock package. So you've got the Sinope dolomite here in green, a Glenwood shale that's too thin to actually show up, but it provides a lot of separation. The St. Peter sandstone, the Prairie du Chien dolomite, and then more sandstone. What we found is that elevated nitrate is a lot more common in this upper aquifer and in the sand and gravel aquifer along the Wisconsin River. These wells are typically shallow and often older. So what did we see? Here's the wells, because I could look at well construction reports and figure out where the well was pulling its water. Wells completed in the Sinope, we sampled 121 of them. 31% exceeded the nitrate standard. The deep aquifer, which is the St. Peter and anything below it, that means the pipe extends through the Glenwood shale and the well is only open to these deeper layers. We sampled 368 wells, 5% exceeded the nitrate standard. Wells that cross-connected, which meant the pipe stopped someplace in the Sinope, and so water could come in from the Sinope and from the St. Peter, we got a mid value, 16% exceeded the nitrate standard. Sand and gravel in the river valley, not surprisingly high nitrate exceedance. And then there was a bunch of wells where I couldn't find well construction reports and they were kind of mixed value in terms of exceedances. Okay, so summary. Karst aquifers formed by dissolving carbonate rock. Water moves fast in these aquifers because of the fractures. Recharge is how you get contaminants into the ground, and aquifers are most vulnerable during the times of the year with recharge. Northeast and Southwest Wisconsin are different, and so we shouldn't try to treat them the same in terms of how the karst flow systems work. In Northeast Wisconsin, thin soils are the really vulnerable areas, and recharge can sort of push contaminants hundreds of feet into the saturated zone, like within a day. In the Southwest, geology and well construction are the important factors in terms of predicting well contamination. And there's the links, and I sent those along to somebody. So I'm going to shut up because I've already talked too long, and I'm going to let Laura go. And I'm going to stop sharing, and we'll do questions at the end.
Thank you, Mo. That was a really nice overview of the karst landscapes all throughout Wisconsin. That was a lot of data too. As we're transitioning to Laura's talk, we're going to launch a quick poll first to collect some of the demographic information from all of you. This anonymous information will help us evaluate the audiences as we're reaching different types of work, and please fill it out because it helps our work. And also just a heads up, as you're exiting today's webinar, you will see a link pop up with one question asking about your experience in this webinar. So please take a minute to fill that out. It'll probably take you less than 10 seconds. Cool. We'll take a few minutes as some of you are still filling out that poll survey. Thank you so much. Okay, now we're transitioning to our second speaker, Laura Paletta. Laura is an outreach specialist within the Agwater Quality Program here at UW-Madison Extension. Laura is located in Green Bay, Wisconsin, and focuses her current programming on ag water issues in eastern Wisconsin, such as manure management and other topics. Laura, please take it away.
Great, thanks, Go Long, and thank you everyone for joining us this afternoon. So Maureen did a great job explaining kind of the background, what Karst is, and why it's so unique. And I'm going to focus on, now that we know, we have maps to know where these vulnerable locations are, what do we do about them if we maybe own land, if we farm on them? So kind of the best management practices to help reduce losses and on these karst soils. And I wanted to talk about this picture. This is a picture I took personally in Brown County, and it really stood out to me because, excuse me, oftentimes driving down the road, you might see some of these outcrops and you see these rocks and may not really particularly jump out to you or pay attention to them. And I know I don't. But this is showing these fractured rocks that Maureen had talked about. And about 10 feet from this ledge, there was a crop field. It was growing. This year it was alfalfa. And so it just really stood out to me that oftentimes we look at a landscape, we see a crop field, but we don't think about what's underneath. And we see how shallow that soil really is, that whatever that farmer perhaps is adding to the crop field, it doesn't have a lot of buffer, that there's not a lot of soil there to buffer when it reaches this rock and these fractures. So I just encourage, perhaps next time you're driving down the road and an outcrop like this sticks out to you, just to really think what's underneath our feet. And so my job is to talk about water quality or agricultural water quality. So again, putting it into perspective what these karst soils, why they're important to agricultural water quality, is, say we're adding manure or any fertilizer, any type of nutrient to the land. It kind of has these two ways to move. So the left here again can be hitting these fractured rocks, going right into our groundwater, or flowing off of our soil, running into a waterway, a stream, perhaps ending up in a lake, here showing Lake Mendota. If that's soil carrying nutrients, phosphorus, nitrogen, whatnot. So kind of two pathways. And why we care. So our groundwater and our drinking water, if nutrients like nitrates end up in our groundwater, they can have an impact to human health. And from the pathogen standpoint, can cause serious health problems. On a surface water level, these excess nutrients can cause eutrophication, algal blooms, like pictured here in Green Bay, which of course impact aquatic habitats, our recreational activities, and can impact human and animal health as well. So very important water quality issues in these areas. So Maureen showed this picture throughout Wisconsin, where the most vulnerable areas when talking about karst landscapes are. So say you're, where you're watching our webinar right now and you do live in one of these areas, or perhaps you grow crops or own land. What do you do about it? What are some steps you can take to be more mindful when you're adding practices to the land? So a couple suggestions. The first is just being aware and verifying the depth to bedrock. So there's a couple ways to do this. Oftentimes farmers use SNAP Plus for a nutrient management plan. And there's a couple layers that indicate the shallow soil there. So they're labeled karst features or Silurian dolomite areas. So again, just making sure those layers are turned on. You can utilize other maps. This is a screenshot to the right here taken of a newer map created. This one just shows the Silurian bedrock along the east side of the state. But this includes a lot of different data layers and kind of is the newest and most precise map we have for the Silurian here. And the link will be added to the chat for you if you wanted to investigate a little bit more. But just looking at other air photos, starting with Google Maps and just seeing what's on your land, if any features stick out that are unique. Again, just investigating a little bit more. And you can also dig up any site-specific information that might be present on your land, if that's a well construction report, manure storage reports, or other drill logs. Maureen did talk about these vertical fractures. So I just wanted to touch a little bit more upon them. So say you do go on Google Maps and you see this unique landscape on your land. So on the left here are those vertical fractures. They're kind of closer together. They might seem to go in every which way. And that would be indicative of having shallow soil. So again, this alfalfa here growing because there's a little bit deeper soil in those cracks that can hold on to moisture better. Compared to on the right here, this shows tile lines. So they're a bit more further apart. They're typically kind of straighter, longer. You can kind of see perhaps where the output is, where the tile line ends. Just again, not to get you too worried if you do see these tile lines. They perhaps might not be vertical fractures. So that's kind of the difference. And it's important to know where the runoff from each of your fields go, right? So this picture here, you see the agricultural field and it runs off into the woods and into this sinkhole. So you probably know your land better than anybody else. So just taking a walk around your field, again, using online maps, trying to find where, when it rains, where does that rainfall move to? And so identifying any sinkholes or karst features when looking at maps, extending out at least 1/4 mile or more surrounding each field. Again, just being aware of your landscape as a whole, not just your 40-acre parcel, but extend out a little bit more to see where that water will move to. And when you do identify these vulnerable spots, utilizing best management practices. So perhaps installing grass buffers or waterways to keep your nutrients and your soil on your field and not entering these vulnerable areas like sinkholes. If you do farm or if you have land on the east side of the state with these, where the Silurian bedrock is, there are standards that NRCS has created within the last 4 or 5 years, NR 151.075. So just being aware of those regulations, those standards, a couple big, I guess, rules to follow. You have to have a nutrient management plan. You cannot spread manure on 2 feet or less of soil, and some other manure spreading regulations as well. So again, just being aware of these standards and following them. And just overall following good best management practices, good soil conservation practices, being a good steward of your land. Again, perhaps utilizing grass buffers, cover crops, reduce tillage. And there's a lot of new technologies out there that helps us be more precise when perhaps putting fertilizer on or spreading manure. So utilizing these precision ag tools helps apply nutrients as close to the crop uptake as possible and helps us, again, maybe spread our manure more precisely and better placement. So I am going to jump more specific into manure because, again, talking about these vulnerable areas, manure already is risky. We talk about the best and worst or riskiest times to spread kind of on this risk factor. And we know to spread manure in the wintertime on frozen soil is the most risky. It's more vulnerable to loss when soil is frozen. It kind of acts like concrete and infiltration is greatly reduced. And Discovery Farms, we do have data that shows a late winter application, manure application, leads to 2 to 4 times more phosphorus losses compared to early winter or no manure application at all. So I'm trying not to spread in winter. And of course, it's risky again with manure, and now add in that factor of these karst landscapes, it becomes even more risky to spread. So I have a couple recommendations of kind of newer technologies that I'm just going to touch upon. If you are interested, please reach out to me. We can always dive a little deeper. I can provide more information. We could even do another webinar upon each of these. So I'm just going to touch upon, again, these new technologies if you do incorporate manure into your system in these karst landscapes. So it would be great to open more spreading windows. I know typically in Wisconsin, early spring, late fall are those spreading windows just because that's what our rotation allows. But what about the summertime? Are we able to go out in the summer and spread our manure then? We have growing crops that can uptake the nutrients. Typically there's more soil coverage and better conditions, better weather conditions. It's drier. Perhaps you can incorporate a small grains rotation that allows summer manure spreading. And there are studies being done, again, newer technologies that allow manure spreading on corn. Ohio and Ontario both have studies that if you spread with a drag hose before the V5 stage, it does not reduce corn populations. And in fact, some have shown an increase in your corn yields due to, again, you are supplying the corn, a growing crop, with those nutrients. So just, again, the research is occurring now, and we can try these different tactics out to lessen manure spreading early spring, late fall type of situations. If you have to spread manure on clay soil, try not to do it when it's excessively dry. Of course, when clay dries, it can create these really large cracks. And again, if you are already on shallow soils, these large cracks could be even a greater pathway to that shallow bedrock, entering the cracks in the shallow bedrock directly into the groundwater. If you can't avoid spreading on your dry soil, a couple of recommendations is to work up your soil, maybe just tickle the surface with some tillage, fill in those cracks a little bit, and apply in smaller volumes as needed. Manure irrigation is, again, another newer technology being tried out by farmers. Overall, it can, again, reduce the volume of manure applied in the spring and fall. It can be applied throughout the summer, delivering these nutrients during peak uptake, again, when your crops are growing and when they need those nutrients. And you can apply in smaller volumes throughout the summer, reducing ponding and other runoff risks. And sunlight is a great way to lessen your pathogens, and sunlight deactivates pathogens. So again, in the heat of summer, sunny day, you're spreading this manure irrigated water, and that sunlight can reduce pathogen impacts. Manure composting, another great way to reduce volumes of manure because it takes out a lot of the water. And it also helps reduce the concentration of pathogens by compost piles get to high levels of temperature, high heat to reduce those pathogens. And when you put the composted manure, back on your field, it adds great organic matter and can influence your soil health. And another plus, it reduces the odor of your manure. Lastly, I wanted to touch upon this on-site wastewater treatment that, again, some farmers are adopting. It is different than the digesters that some farmers have on their farms. So it kind of ends it's a different process and it ends with a different output. So it's whatever, your goal of your farm is to which system to utilize. I just wanted to touch upon this wastewater treatment. People might not know as much about it. So it goes through a different process. And this table here was taken from a farm on the western side of the state that implemented one of these treatment plants. And you can see clear water, clean water, 40% total by weight. That's the product. So again, just different products, different ways to minimize the volume of manure that you have that you need to spread on your land. And again, when you're on these really vulnerable areas of karst, reducing the volume could be the first step to really, reduce your impact on what you're spreading and what you're adding to these karst landscapes. So to sum up, some key takeaways, again, just overall karst topography is more susceptible to water contamination, right? Maureen showed that they have these rapid recharge. She shared why that happens. And when water or manure in this case kind of hits those fractures, it rapidly can get to our groundwater and our drinking water. So when farming, follow all rules and regulations, be aware of these sensitive spots. Of course, being aware of these locations is the first step, and then choosing better practices on those vulnerable areas, and perhaps prioritizing pathogen movement is the first step too, to make sure those pathogens don't reach the drinking water, and then utilizing soil conservation practices following the NR 151 standards that talk about erosion, tillage, manure, etc. And be particularly mindful if spreading manure. Again, spreading manure is risky, and now on these even more vulnerable areas, it's even riskier. So perhaps utilizing one of those new technologies I just shared to overall reduce the volume and impact pathogen content, etc., can just help overall reduce impacts. And sorry, I feel like I went through quick, but I wanted to make sure there was time for questions. So there's both of our emails, and I'd be happy to answer some questions.
Thank you, Laura. That was a great presentation. And now I think we'll just go straight into the Q&A. And while we're doing the Q&A, we'll also pull up the QR code for the CCA credit for the session. So if you cannot scan that, please feel free to type that in the chat and we'll enter that for you. Well, first question pops up, and I think in most presentation, when we mentioned the SWIGG study, one question was asking, did the SWIGG study results suggest that land management in the area of 40 acres around a private well influenced water quality?
Yeah, so there are several objectives in the SWIGG study, and one of them was to look at land use characteristics directly around the well. And so I actually went, back and looked at that study, and I'm trying to find my report here. We looked at different radii, so like 750 feet and further out. And indeed, the land use directly around a well does impact the water quality around that well. I mean, it's not surprising. I did some research at Pioneer Farm, where there's a whole network of monitoring wells, and right at the top of the ridge where you have strong downward hydraulic gradients, the nitrate is really high. It's like 45 or something, right? So right around your water is, the water coming into a well is just coming from, wells don't have huge capture zones. You're only pumping 15 gallons a minute, enough to supply water to 3 or 4 people in a household well, right? So you're pumping maybe 150 gallons a day. That water is going to be recharging right in the area around that well. So yes, that is indeed correct. And if you'd like to look at that, I put in the link for the SWIGG study in the links that I shared. And objective 5 is where your question is addressed. Josh, does that answer your question? Can Josh talk, or do we have the participants muted?
I don't think Josh can talk, but I'm supposing Josh is nodding.
Okay.
Hey, there we go.
And it looks like another one For me, NR 51, oh no, Bedrock less than 2 feet. Do you feel the distant Bedrock is too low when considering fertilizers? Anonymous attendee. Certainly, you can't spread if it's less than 2 feet. The thicker the soil cover, the more protective. We didn't really start to see a change in water quality until we got to about 20 feet of superficial sediment. But 2 feet is a good starting point, and there's a reduction in what you can spread, from if you have 3 to 5 feet of soil, you can spread less than if you have 5 to 20 feet of soil. So it's a starting point. Whether it's entirely protective, that is a question I'm supposed to be trying to answer right now. Unfortunately, due to state budget snafus, the funding for that project that is looking at the effectiveness of the NR 151 code lost funding in July, and I'm trying to secure new funding for it. So maybe in 2 years, I'll have a better answer, but I don't right now.
All right, thank you, Mo. I saw a question talking about manure composting. Laura, how does manure composting influence emissions of greenhouse gas? And can you talk a little bit more probably about its impacts on water quality as well?
Yes, definitely. Great question. Of course, there's positives and negatives to each of those kind of newer technologies I shared that I did not get into. I don't have a specific number, about the greenhouse gases, but I know, yes, there would be some impacts, especially with the manure composting. Like any kind of practice, there are those pros and cons, positives and negatives, trade-offs we have to weigh out. So, with the composting and each of those kind of newer technologies, that's, again, something we could dive into another time and just what's right for your system, your farm, and again, what your goals are.
Absolutely. And this is probably a question for both of you. One of our participants asked about legacy nitrate. They were specifically quoting a study from Casco Village in Kewaunee County. Can legacy nitrate be a source of nitrogen showing in those monitoring results?
That's actually, I can answer that one. So Davina Bonas in the county has shared with me the Casco nitrate study results and has asked me to comment on them. The consultants who did that study are very good isotope geochemists, and they've sampled for isotopes and for tritium and said it's old water. But what's actually complicated about a well in a carbonate aquifer is that you have two kind of pathways to it. You have a very rapid pathway, which is the fracture network, and I was showing you results that sort of show the impact of the rapid pathways. That's how you can get contamination at that one homeowner's well so deeply, so quickly. There is also movement through the fracture blocks that is much slower. And so when you just pull a sample, you're mixing those two water sources. And there was a great study that a USGS scientist, United States Geological Survey hydrogeologist, did out in a different carbonate aquifer out in the Dakotas, where they ran a tracer test where they put something into a spring. They used a dye, and then they detected it at a well like 7 days later. But all of the age dating methods for groundwater, like tritium or chlorofluorocarbons or other things, suggested ages that were more than 30 years old. And so you can't just take one line of evidence. You really have to think about both when you're thinking about vulnerability. So yes, there are probably some legacy impacts. There's probably also some rapid pathways. You can't say it's all rapid or all legacy. It's a mix. And I think of the scientists who did the Casco study, they're only relying on their isotopes and the tritium to come up with the fact that it's all old water. And I would disagree with that based on other data from the area. And they didn't do anything, they didn't do any kind of sampling that would identify rapid pathways.
Mm-hmm. Thank you, Mo.
Yeah.
And I have an extra question, talking about sinkholes. I think both of you mentioned sinkholes in your presentations. Where does water come from or go to in those sinkhole situations? Groundwater, surface water, a combination of both?
Both. There's a classic sinkhole up in Door County called the C&M sinkhole, where this stream from Gardner Marsh comes into this farm field right near those two county highways, and it vanishes in the ground. And then it shows up seeping out of a hillside at a farm about 2 miles to the west. In which case, so it went underground and then it came out again as a stream, right? Sinkholes go directly to the groundwater system. They go to the water table and enter the groundwater system. Now, how that groundwater comes out again, it could discharge to a stream, it could discharge to another spring. But yeah, sinkholes basically lead to groundwater. And how they form is you have soil, and then you have this fractured rock aquifer, and there's all these vertical and horizontal fractures. And let's say there's a horizontal fracture down there, and it takes a lot of water, and then as it gets bigger, it can take more water, and you just start dissolving more, and eventually you get like a void in the subsurface. And when the top collapses into that, then you have a visible sinkhole. But there is a void underneath that's present before it collapses. Does that make sense?
Mm-hmm.
Okay.
Yeah. That was really helpful.
Are there building regulations? I don't think so. I know that people who know they're in karst areas will sometimes contact our agency and say, what are methods of trying to detect sinkholes? I know, for instance, right now, Madison Metropolitan Sewage District is looking at putting in a new sewer line, and they're working with a geophysicist in our office to try to see if there's any kind of karst underground voids in the area where they want to put that sewer line, because you don't want it to collapse and have a bunch of sewage go into the aquifer. So there's not rules, but sometimes, at least if it's a government funded project, people will raise the concern, like citizens or whatever, in a public meeting, and it needs to be addressed, but I don't think we have rules about it. I'm also not an expert on building code, so I wouldn't take me as legal opinion here. Right? So,
absolutely. I think that's all the question we have for now. Hopefully you have scanned the QR code for the CU credits if you're looking for something like that. I'm gonna start sharing screen to kind of finalize our final message today. This is our second webinar for this year, where we talked about karst. In 2 weeks, we'll talk about soil health practices impact on phosphorus pools and availability. In a month, we'll talk about grazing and water quality and some of the lessons we learned from agile field monitoring. Okay, thank you guys so much for joining us today. On your way out, again, you will see a question asking you about your experience with the webinar today. If you would like to share the recording of this webinar or any other webinars in this series, please let us know, and I think we'll distribute an email with all the webinar links to all the registrants by the end of this series.